everything is working fine. Let's start. Yeah, speaking of this question, we have the time complexity of this approach was O of n we because at any point of time we are either keeping the node or either keeping the node or either removing the node. So that's why it's O of n. So if we want to keep, so if we come over here, we keep the node, or we at this point of time we remove the node, and every other node is kept. Hence, the time complexity is n because every node is visited once, and space is also constant because there's no extra space involved. Okay, now coming to this question, this is merge case sorted lists. So what you're given is a vector of different lists, and right here we can see there are different lists, and you need to merge them. So let's first of all look at what you would do if you have two lists and you need to merge two lists. So in that case, you simply create a dummy node, and you have a and what you do since you have two lists, so you know using a similar concept of merge sort. Using a similar concept of merge sort, what you can do is you can compare the elements one by one from each of the lists. So if you compare right now, you can see you can see that one is smaller. So I'll link the dummy node with one, and I'll move the red pointer towards the next node. Okay. Now I'll do the comparison again. Two is smaller, so we'll we'll advance um, our current pointer. So initially the current was right here. So we linked current with one, and after that we advanced our point. Sorry, we advanced our pointer to here, and we linked current to 2. So after doing that, we'll move our pointer next towards next red pointer, and we'll move our current one step ahead, whatever we have chosen. At this point of time, at this point of time, we see that 3 is smaller, so we'll link the next of 2 with 3, and hence our current pointer moves towards the next. That is 2 dot next. That means right here. Then after that, since we have chosen something from here, we'll move our pointer towards the next position. So this series is gonna go. I'm quickly gonna do the same thing. At this point of time, 4 is smaller, so 4 is smaller. So this will be chosen, and the current pointer will be linked to this. Sorry, and the current will go one step forward, and this will go one step forward. 5 is smaller than 6. 5 and 6 are compared because these two are the pointers which are involved. So you can compare, and 5 is smaller, hence 5 is linked to it, which makes the current pointer goes 4 dot next. That means right here. Okay, and the red pointer moves one step ahead. So basically, current is right here. This point of time comparison is made, and 6 is smaller. So what we can do is we will link the 5 dot next to the blue pointer what we have, and we'll move the current pointer towards the next position. Then after that, since we chose this, so we have to move the blue pointer to the next position. Now at this point of time, we need to choose between two. 7 is smaller, hence we will simply do 6 dot next, or the current dot next. Basically, current dot next is equal to whatever red pointer is, red pointer. So this operation is basically, if you see, current dot next is equal to red pointer or blue pointer. Okay, so wherever the current is present, I'm linking the next of current to either red or either blue. So either red or either blue pointer. So that's the whole operation I'm doing. Anyway, let's carry on with this. So since I linked this with right here, it goes to null. Now this point of time, I have null. I have one red pointer pointing to null and blue pointer pointing to 8. So it's obvious that the rest of the remaining elements which are present in blue are greater than till now what we have iterated through. So we'll just simply link the of course we have to move the current as well. So current moves ahead. So now what we need to do is we need to link the current pointer current dot next to blue pointer. Simple. And rest of the links are automatically we don't you don't need to change it any further. So if you go through from the very beginning, you can see start from here 1 2 3 4 5 6 7 8 9 and none null. So that's how you link. You have two lists here. So the time complexity of it is actually suppose the first list contains n elements and the second list contains m elements. So the time complexity of this whole would be n plus m. Why? Because because you are iterating through every node, or not sorry, m plus n basic. You are iterating through the first list till here, and also you are observing every element till 8, and after that, like whatever you are doing, it's directly linked. So I think the time complexity should be uh, minimum of n n comma n n comma m. Come on, yeah. So this is the time complexity, and into two because that's how many nodes we have seen. All right. So, but this is a little tricky when we come across multiple lists. So we need to merge instead of two, we need to merge multiple lists. So how do we do that? And if you observe, so I'm just going to discuss. Sorry, I'm just going to discuss time complexity of every possible case. Let's see if I have, if I have maybe one node right here. Okay, I'm not gonna write the number. So let's not do this. Okay, so this is one list having the dots as one node. Let's say. Okay, and we have finally the last list is over here. Okay, so the approach would be using the same approach. We can actually club these two linked lists to form a single linked list, right? So these two linked lists will be, so suppose these are k linked k linked lists which we are given with. So if we combine these two linked lists and form a single linked list, and let's say the output would be any, let's say the output would be 1 2 3 4 4 from this, and total elements would be sum of those two linked lists, right? So we have basically sorry, basically merge these two linked lists into the new linked list. Okay, then we're going to do the same thing for the rest of the ones. We're going to merge these two linked lists. We're going to obtain one linked list, and then we're going to merge with with the remaining linked list. So we are clubbing them to uh, making pairs of two. So if we so how many comparisons and how many um, comparing we are making is, if you link this one with this, so that's going to make it uh, one grouping that takes that takes n time, right? That takes O of m linear time. Okay, then we are merging this linked list with this linked list, the resultant linked list with the next linked list. It takes another n time, and it takes and then we are merging this linked list with the resulting linked list that also takes n time, right? So if you can see, there are 1, 2, 3 and 4 linked lists, and the possible merging by comparing two linked lists are 1, 2 and 3. That is k minus 1 times. So k is equal to 4 over here, and the merging two linked lists takes O of n time. So merging of k linked lists will take O of k minus 1 n into k minus 1 times. Why? Because it's one less summation is going on. So it's virtually equal to n k minus n into k. Let me write with this another color. This is n into k. Okay, so remember this, it's important. We'll be using this in later on. But so, but another, okay, so it's a into k. Another approach would be, to, let me copy this linked lists. Okay, so another approach would be right here. Oh man. Okay, another approach, let's discuss it right here. Okay, so you don't need this, 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 and you don't need this. Anyway, so we have the same thing. What we can do is, using the same approach what we discussed in the two. So we will have 4 pointers, and we'll compare whatever the smallest among this is, and we'll link it to the another separate linked list. Okay, once we are done with comparing this, suppose this one was the smallest one, so we will move our pointer towards the next position and compare these four values. So let's suppose we find that this node is the smallest among those four. So we'll be linking this node towards another point in the output list, and we'll be moving our pointer towards here. Okay, but you need to observe that over here what we are doing is we are comparing what is the smallest element possible among this four, right? This four as in this k element, these k elements. Okay, so let's suppose you are let's suppose the entire list is made of the out of merging these stuff, and the total number of nodes are n. Okay, so total number of nodes are n in the output list. So to form each list, each node, sorry, we had to compare all these four elements, all these k elements, and find out which is the minimum one. All right. So to do that, we can use a simple, linear searching. Okay, we can have a min variable, and we can keep on checking that is this the smallest element, 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 and so on. So it's basically checking every element and storing that in a min value. Whatever smallest element we got, we will be just inserting into the linked list. So that's how we are generating every node by linear comparison, and the linear comparison takes O of k times. So basically O of k times is generation of one node, or generation of one node. So let's zoom out a bit. So since generation of one node is O takes O of k times, so generation of total number of node, that is n, will take n into k times, into k, n into k. That is the time complexity of this approach. So where you are comparing the minimum, you're getting the minimum value from linear comparison. Okay, that's why it is. So this is one of the things. But this is also slow. We need to improve it further. So now this is where heap data structure comes in, right? So the time complexity is increasing, or it's still n into k, or you can say if n and k are equal, so it's similar to quadratic, right? It's similar to n square if n and k are similar. So to reduce the time complexity, we observe that over here finding the minimum element is a little tricky. Yeah, so finding the minimum element takes O of k times. Can you reduce that? Yes, we can. We can use a heap data structure to do that, right? So if we just so if we come over here, um, now, so what is a heap data structure? Let's first study that, then we shall move on to how to solve the problem. So first you need to know what a heap is. So just a quick, I you know question: are you aware of what heap is?
Yes.
Okay. Okay, since I'm recording and I'm doing it, I'll just briefly walk you through it. Anyway, so the heap data structure is some sort of you can imagine is, I won't be going to details how the heap is implemented. I will be just explaining what's the time complexity of addition and deletion in a heap data structure. That's it. Based on that, we will be calculating the time complexity of our approach using the heap data structure. So it's just for that. No implementation will be covered in this lecture. Anyway, let's move on. So over here, this is a mean, and this is a min heap data structure. Now, what a heap is basically alignments of data structures in a in a sort of like a tree fashion. So if you don't know tree, it's basically if you can access the data, if you are at one data or one node, you can say where you have one data, that node has two childs. That's a tree. And in a heap, the arrangement in such a way is in such a way that the element at the one level over here, that is called the parent level, is either smaller than the elements in the next level or greater than it. So if the element is smaller than the child elements, then that is called a min heap. All right, that's a column in heap, and it doesn't matter that this one should be smaller, like before 2 on the left hand side a smaller value should come. No, it's not necessary. The only condition for a min heap is having having the parent value smaller than the child value. That will create a min heap. Let's look at a max heap. So a max heap is slightly just the opposite one, having the having the having the parent level smaller than all of its child values. That's what max heap is. Hmm. That's what max heap is. And since like it doesn't matter, the order doesn't matter, all it matters is the child and parent level comparisons. So for this question, we will be focusing on min heaps because, and I mean, we'll be using min heaps, and the reason for doing is that min heaps since the property of the mini heap is that the parent level is smaller than the rest of the tree, rest of the children present in the tree, or greatest or smallest, so we can use that property. Okay, right here the parent level is this one, which is smaller than the all of its child value. So we can simply extract this value, the minimum value, out of every value. That way we can minimize the o of k to o of 1. Right, we'll look into that later on. Let's explore the heap data structure a little more. Okay, so looking at right this a heap data structure is having the, now how do we implement it? I'm not going to show the code, but I'm just going to tell you what goes in the background. So we have an array with which we implement the heap. And the way heap is structured is, first you come across 2, then you come across 7, 5, then you come across 10, 11, and you go on. So then if in case you want to include a next element, in case you want to include any other, add any element, so you have to add over here, because this is the flow. The next element would be coming in this flow. So if maybe let's you are supposed to add 3, so 3 would be coming right here. You would add the element here, and adding the element here or any other position other than this, if this position is not filled up, it's not actually how heap works, because that destroys the property of heap and we can't use it. So just imagine that the heap is working like that. So you have to insert to the next empty position where the flow is going on, right? So we won't be dealing with addition or deletion. There are inbuilt function which we'll be using in our code, so we don't have to do this. But the understanding of how heap works and will make you understand what's the time complexity, why the time complexity is so. Okay, okay, so let's just see right here. So if you can see, the now they are mapped in a array, right? So 2 is mapped with 7 and 5. So 2 is let's go a little down. So 2 is mapped with 7 and 5. Then 7 is mapped with 10 and 11. So you can say 10 and 11. Then 5 is mapped with, then 5 is mapped with 6. So the 5 value is mapped with the 6. Now, if you want to include any extra element right here, that will be mapped to 5. That means that's going to be that's going to be that's going to be mapped towards here. So let's say if you introduce a new 3, so 3 is going to be introduced in this array in this format, and so on. It's going to be, next element that's going to be inserted in the array. So this is the, in background, this is how heap is implemented. Okay, so I guess that's what heap is. You have the idea. So we won't be dealing with the array portion. We will be just adding elements and deleting elements. So let's see what's the time complexity if we add and delete element. Let's understand that. So like I mentioned, we add only we add elements only at the the flow. So the flow is going right here, finally coming here. So the last element is here, so we are going to add right here. So let's suppose, okay, so let's suppose we have, just a second. So let's suppose we are adding some elements in the heap and we want to add. So the next element we add, let's say it is 2. So the property of heap, before doing that, you can observe that every element is smaller than the child elements. You can check at any point of time, any point of the heap. 11 is smaller than 12, 15, 17 is smaller than this. So it doesn't matter, like right here it is 17 and to the right side it is 26, then 11. So this order doesn't matter, right? Level wise, order among the level is doesn't matter. What matters is parent and child order matters. Okay, so it's if it is a min heap, so every element must be greater than the child elements. Okay, so it is property is maintained. So if you want to, if you insert any random element, so obviously this element is different from 70 or whatever the element is present right here. So this disturbs the heap property, right? So what you need to do is you need to move around some values so that you can make the entire heap more proper. Because if you see at this point of time, if you have inserted 2, the smallest element sh- should be at the top, but it isn't, because 2 is the smallest element, because 2 is the new smallest element among the whole tree. So this is not the correct way. You need to change it, modify it, and that process is called heapify. I'll be using the term called heapify. It's heapify. Yeah, yeah. Anyway, so that process is called heapify. So how do we do that? We just compare 2 with 70, because since 2 is added, so 70 might be affected, hence we need to check it out. And yes, 70 is smaller. But let's suppose you added 100, right? Let's suppose if you added 100, you compared 70 with 100, so it's okay, it's fine. 70 is smaller than 100 and the heap is maintained, so there's no further swapping done. But we need to calculate that, we need to understand the time complexity, so I'm inserting a 2. So if we insert a 2, 70 is greater than 2, we need to swap it. So what we do is we just take 70 and we take 2. Now we don't need to further check for 80, because if 70 was smaller than 80 and we are replacing it with an even smaller number, so we don't need to check about from here or left hand side. Okay, let's move on. So 5 is less than 2. Yes, we need to swap. So 2 comes here, this gets exchanged, 5 comes here, and 2 comes right here. So at this point of time, again the same logic, that 5 was smaller than 11 and you are replacing 5 with a even smaller number, so you don't have to compare it, and you just move on to comparison of to the top. So you can see right here, you can observe that at this point of time, what you did is you didn't check the left tree, and you simply moved towards the topmost tree. Okay, at this point of time also, you didn't check the left tree, that's only one value. Right here it's 3 value. Okay, so you just move right here. So if you can observe, then 2 is indeed, sorry, so 2 is indeed smaller, so 2 comes at the very beginning and 3 comes right here. And again the same logic, 3 was initially smaller than 4 and we are replacing 3 with 2, so we don't need to compare it. And like, if we not if it is obviously smaller, the whole entire the tree also is isn't affected. You can say if this node is not affected by this node, then it's for sure that the rest of the nodes are not getting affected. Okay, because if there's a smaller value at the top than this, then it's for sure that these values are even bigger than that. Anyway, so it's pretty obvious why we don't need to do that. So at this point of time also, what we are doing is if we make a line like the previous one, we are ignoring this whole particular tree. Correct, we are ignoring a whole particular tree, and after we included a 2 inside, added a 2, then we checked a 2, include a half part of the tree, check, then replace some other, make made more swapping, did more swapping, and ignore half part of the tree. So it's giving us a feeling that it's some sort of a log of something complexity, right? And if you observe that you are comparing, you're swapping one time, you're comparing one time, then two time, then three time, right, until you reach the topmost. So it's basically, you can see that the comparison is basically the what is the height of the tree. That many comparison is going on. So let's see what a height of a tree is. So just a quick introduction to what height of a tree and how is it calculated. Suppose the element of the suppose if it is if there are one elements and if the no if the parent node has two elements, then okay, so then this node has further. Okay, so this at this point of level, only one element is present. If it has childs, two elements are present. If it has childs, four elements are present. If you can go on further, let's just do it. Okay, this is just to calculate the height of the tree. So height of the tree, that way it's much clearer. So we can go. Oh man, that's so. Okay, now what we can see here is that at the very topmost position we have one node. At the very second level we have two nodes. So at the third level we have four nodes, and at the fourth level we have eight nodes, and so on. It goes increasing. The next node would be 16, and so on and so on. Right. So what we need to do is at wherever we are at, can we figure out the height of the value, height of the tree, right? If we have suppose these number of elements, can we figure out this? So actually that can be figured out by the total number of the total number of nodes. Let's say suppose maybe so there are like four nodes. Okay, so you can just see that 4 is equal to 2 to the power 2, 2 is equal to 2 to the power 1, 1 is equal to 2 to the power 0. Okay, and it just goes on. It's dividing into this thing. And the height at this, let's take any level. So the height at this point of time is basically 3, right? 1, 2 and 3. If you let's check out like any other value, at this position is 2, 1 and 2. So it's literally the power of what 2 it is, whatever 2 we have. Okay, so if I have 8 is equal to 2. Okay, so if we have 8 to the power 2, 2 to the power 3. So if we do log at both sides, log of 2 base of log of 3, sorry, okay, log base 2. If we do that, we can figure out that we can the log due to the log property. Okay, let's remove this, it's creating a little so due to the log property we can say that 3 comes right here, and this becomes 1. So this goes out, and 3 is equal to log of 8 to the base 2. That's the height. So basically 3 was the height. So to calculate any if we generalize this formula, so log of base 2 number of nodes. So number of nodes at the at that level, let's say over here was 8, is equal to height, right? So, and if you just see it, the number of nodes are almost you know total number of nodes and the number of nodes of the leaf node are okay. So the total number of nodes and the leaf nodes are almost similar. So you can just say that whatever um, nodes are there, so the total number of nodes, what you do, so the height of the tree is basically the log n base 2, right? So height of the tree is basically log of total number of nodes um, to the base 2. So when we come at here, we saw that the we saw that if we inserted a 2, it it was equivalent to the number of swapping was equivalent to the height of the tree, right? So since this was 1, 2, 3 swapping, and the height is also 1, 2, and 3, so the number of so basically if we add one element to the heap, the time complexity of heapifying the heap would be log of n, that is the height. Okay, so that's the heap, that's the time complexity of it. So let me write it down with another color, although it's obvious that's, but log of n, let's say, at this point of time, that's the time complexity of heapify log of n, that is the height of the tray. So adding any element takes log n time, and you can see the deleting also takes a log of n time, and how I'll show you in a minute, and this will be much quicker. So you see how you want to delete it. You want to you want to swap the 80 with 3. Okay, so what you're going to do is you're going to move the 3 to the bottom, and you're going to move 80 to the top. Let's just move it a little. Just a minute. It's going to be, yeah, much better, much cleaner, much better. Yeah, so what we're going to do is we are swapping the 80 and the 3. So 3 comes right here, and then we chop off the 3 and we delete that. Okay, that's how we take a minimum value from the top. How we just swap it with the last element, and then we take it. That's how what goes in the background. That's what goes in the background. Once we remove it, we use that value, and um, and that's what it is. Just before doing that, let's just do one other thing. Other thing. So we can do is if the 3 was, why it's not moving? If 3 is right here and 80 is right here, so we can do is heap dot top, which yields us the minimum value, right? And if we do heap dot pop, that means what we're going to do is we just replace that. If you replace 3, swap 3 with 80, and then finally removing the 3, which is at the very end, that's what popping is. But after doing that, we are not done, because the heap is to be, heapify function is yet to be done, because 80 is greater than 4 and 5, so you need to do that. Okay, so at this point of time, what you're doing is you're comparing 80 with two values, 4 and 5. So 4 is the smallest, so that will come to the top. Okay, so 4 comes above, it becomes 80, right? And at this point of time, you're not worrying about this, because you know that um, 4 is smaller, and yeah, then you come on to 80 and 17. Then you see the 17 is smallest, so 17 goes to the just a second. Yeah, so what you do right here is you are comparing 80 with 4 and 5. Okay, so whatever the minimum is among these two, that will come up. So if I replace 80 with 4, then the idea was I don't have to worry about this whole tree, because 5 and 4, among 5 and 4, 5, 4 and 84 is the smallest. So if 4 comes above, we know that the rest of the tree is already heapified and we don't need to worry about that. That's why we are doing that. Okay, so that's why we're doing. So if we replace 4 with 80, 4 comes at the top, here comes at 80. Now we're again going to compare, and between 17 and 26, 17 is the smallest. So what we're going to do is you're just going to replace 17 and 80. Okay, okay, so while we were here, we ignored this part, right? And then what we're doing is 8 is right, sorry, 80 is right here. Then again what we're going to do is, now after this operation, this tree is ignored because of the fact that we're not checking at here. Then 80 is checked with 28 or 23, and 23 is the smallest. So what we're going to do is we're just going to 23, and that's 80. So that's how we're doing. And like the addition one, over here also we are we are excluding the part of the trees. That gives us an idea that it must be some sort of a log n operation. Okay, let's clear this out and let's see if we go from here. So we made a swap. Sorry, yeah, this is one of the, why is this going? Yeah, so this is one of the swapping which we are going to do. Then we did swap right here, then we swap right here. So as you can see, 1, 2, 3 swapping, and it's almost similar to the height of the tree. So height of the tree. So the number of swapping we did is log of, and that is height of the tree. Okay. So if we want to delete an element, it takes log of n time. That is n is where n is the number of nodes, basically height of the tree. Right. So if we deleting an element, it takes log of n time. If you are adding any element, it takes log of n time. Right. But the only but if we want to just, if we have a heap like 5, 3 and 4, we want to just know what is the minimum value of the heap. We just simply go at the very top, and then we can say that. So retrieving the minimum value takes O of 1 time. So that's the whole time complexity analysis. Okay, finally we have done. So let's move on to the other approach which we were talking about. Right here, what we did is we were merging k lists, and merging k lists take, since we are comparing 4 elements, it took linear time. That's why we are having O of n dot k. But if we use a heap data structure to, like, suppose we have, maybe, okay, so, and last one, come on. So if we use a heap data structure to, let's say this is the one, then this is the one, this is the one, and this is the one. Right, we are at this point of time, and like I discussed in the just in the previous approach, what we are doing is we are comparing these elements, and then we are formulating the whole list. So for this approach, what we can do is we have k lists, and we can modify the time complexity by using a heap. And so in a heap we have k elements, suppose. So we can make the heap of a k elements, you know. So if we add every element to the heap, let's say, if we add, then retrieving the information would take, okay, before doing that, let's just write it down right here. uh, addition addition takes O of log n time, right? Deletion takes O of log n time, and find minimum value takes O of one time. Yeah, so these are the values. Okay, so if we add every value, suppose at this point we have every value in the heap, and if we want to find the minimum value, so what is the minimum value which we can find? I mean, what is the time complexity of the finding the minimum value? Let's suppose the next minimum value is the top one, right? Time complexity is O of one. So the next minimum value which we will get is by having a O of one complexity. But there's another thing. Suppose this was the minimum value. So what we do is we we move our pointer towards the next node, and we want to add that value to this. Okay, so this was the previous value which got inserted in the list. Okay, so we knew that this value was at the very top, which we inserted right here. Okay, so we looked at it and we inserted it into it. It costed O of one time. But since we are done with this element and we need to move on to the next element, so what we need to do is we need to delete this element first, because we have already used it and we don't want to make comparison using that. So we will delete it. So that will take log n time. Log n time, or what? It, since the number of elements in the tree is k, so it will take log of k time, O of log k, because you are using, you are obtaining elements, one element from each list, right? One element from each list. That's why k elements. So in the heap, total will be k elements. So deleting would be having O of log k times. Now deleting is okay, but after that, after deleting it, you are going to add another value, right? Add another value so that the number of elements still remains k and you can make comparisons. So adding takes O of log k time. And why it's taking, like, because there is a heapify function going on. And if it, because we don't do the heapify, we won't be able to pick the minimum value in O of one time. We have to traverse the tree. So heapify goes on. So the whole co- complexity of, adding one number, deleting one number, and adding one number, that takes 2 into log of k, right? Now if the list is supposed fully made, total number of elements are n. Total number of list elements in the list are n. Okay, now, so for making a node, you had to delete an element, and add another element, which took to log k time, right? So that's for one, finding out one element. So for um, generating every node in the final linked list would be n into 2 log k, which is equal to O of n log k. Yeah. Okay, so that's the complexity, and um, finally we derived it. Why is it O of n log k? So that's why we are using. So the whole concept is very easy. Just just with, in spite of comparing, instead of comparing in a linear fashion, which was giving O of k, we reduced it to log k. That's the whole difference. So n remains same, just the k is differing, right? So every node is generated. That's why n is that. And to generate each node, it takes log k time, because we're using a heap. That's what the difference is. Any doubts till here? because this was the whole explanation.
No doubt.
It's okay. It's pretty clear, right? Okay. Okay. So this one is the usual approach which people do that takes n log k time, but it's a little you can say um, it's okay. You can implement this, but I'm going to do a little more easier to understand and easier to implement version. So what I'm going to do, so what my approach is would be, if you have k lists, let's say you have k lists. This is the you can say the fourth approach we are discussing, and that's what I'm going to show you the code of. Okay, so the previous approaches, what they did is they compared, they took values from the lists and made a heap out of it, right? They made a heap out of it for maybe, let's say, k elements, k elements total, because taking one element from every list. but but the idea is, since you are deleting one element and then adding one element, so virtually what you're doing is you're using a heap data structure to add every element in it, add and delete elements. So instead of doing that, why don't you just why don't we why don't we simply add all of the elements in the list into the heap? So let's suppose, so is suppose the answer of the output list has n nodes. So if this list consists of let's say a nodes, this contains b node, this contains c node, this contains d node. So the output list, let's say, suppose it consists of total number of n nodes. So it's basically a plus b plus c plus d, let's say. So instead of picking one nodes from it and making a heap of that, making a heap of k elements, instead of make heap of n elements. That way you don't need to further worry about addition and deletion. So you can add all the elements at once, right? So this they will be present in a big heap fashion like we discussed right here. So instead of having a heap of 4 or 5 values, we'll create a heap of all the n elements. And after doing though, where was it? Where was I? Yeah. So 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 adding making a heap of n elements, I can simply pop the smallest element among the all elements, right? So once I have every element in the heap, I can pop the smallest element, pop the smallest element. Oh man, yeah, pop the smallest element right here, put it in the output list, then heapify it. Now heapify would take a log of n times, not log k, because here the number of nodes are n. Total number of nodes in the list are n. So it takes log of n time. Then we move forward, and we again pick up the minimum element. After deleting one, we pick up the minimum element, and then we heapify again. So it again takes log of n, right? So it goes on after every. So addition would be taking, we'll be adding one element to the heap, and heapifying it would take, addition takes log n time, that is addition, and the deletion takes negative time, because we are deleting and adding from the new elements, right? So let's give me a quick example what this means, just a short example. So if I have 1 2 in the list, so 1 2 in the list, and if we have 3 4 5 um, 2, not so 2, let's say it's 6, right? So I'll be adding every element. So one we'll add 1, then we'll add 2, then we'll add 5. Okay, then 5 will get added. Okay, we'll traverse the list and 5 is added. Then we add 3. It's okay, fine, because it's a min heap. Then we add 4. Then we add finally 6. Correct. Now, after having a min heap, although this didn't require any, mm, let's change this value to 3 and this value to 2. Let's say, okay, okay. So this is 3 and this is 2. So adding 1, then we add 3, then we add 5, then we add, then we move towards from here to here, then we add 2. Then we need to heapify it, right? Which will is going to take log of n time virtually. So adding is taking log of n time. So we heapify it. This goes to 2, this goes to 3, and it's done. Then we add 4, which is going to get added here. Then we add 6, right? So at the end we have a heap 1, 2, 1, 2, 5, 3, and 4, and 6. At this point of time, we don't need to worry about the individual linked list because we transferred every linked list in the every element in the heap. So took one element. Transferring one element took log of n time, and you totally transferred n elements, right? Total number of elements which got transferred was n. So the addition takes making the entire heap takes n log n time. Okay. Now to make the list, we're going to delete one element one by one. And as we know, deleting elements take log n time, deleting one element. And we're going to delete one by one every element. We're going to delete one, then two, then three, then four, then five, then six. After we need to heapify after deleting. So every element takes going to take log n time deletion, and hence the total number of complexity would of deletion would be n log n. So the net complexity for this would be 2 of n. Let's write it with some other color. 2 of n log n. That is virtually equal to of n log n, where n is the number of nodes in the output list, the total number of nodes. That's the time complexity. So I'll be explaining, or I'll be coding out this approach in quickly coding it out. It won't take much time, right? Then we'll do it. I think this approach is clear, right? The whole approach, adding
Yes.
every element to it instead of adding k elements. All right. So we have two steps. We will first. So the first of all, we'll need a priority queue. So in C, I'm coding in C++. What's the priority queue? So the way we declare a min heap priority queue is basically vector int greater spelling यही होती है ना, हाँ यही होती है, sorry, and min underscore heap. So that's how priority queue is declared. Prior. Okay, so we're done with that. So step one is push all the nodes to min heap. That's what you want to do. And the step two is uh, delete nodes. Uh, you know, pick minimum value and add to, or you can say, delete each node from heap and add to uh, put list. That's what you want to do. So it's just simply two-step approach, two steps approach. So the first thing what we want to do is one other thing, small thing to implementation for the C++ over here coders is that this is a list of this is a vector of list nodes. So what this means is you have a vector and every element in the vector is pointing to a list, right? So it's a pointer basically. So if you have a list right here that goes, you know, goes right here, that's what these pointers are doing. So what you need to do is you need to traverse this list, you traverse this vector, and then finally traversing the individual list and adding the elements. Once you're done with that, you move forward and add individual elements in the this list. That's what vector and list node is about. So I'm just going to quickly do that in C++ language. Just a second. Hold on, someone came. Okay, never mind. Yeah. So I'm going to do a for auto loop, auto pointer, and auto one is used for. So this auto is used to iterate. This pointer is used to iterate in the vector, right? So the vector is getting iterated, and at every step we need to go further down. So first is like vector one. First is like vector of 0, then sorry, the lists of 0, list of 0. So this one is the list of 0, and then we're going to go inside it, right? So that's what's going on. So the pointer is having list of 0, list of 2, list of 3. That's what's going on. So doing that, and after that we need to move downwards. So for doing that we will use uh, pointer not equal to null, doing that, and now we are iterating through each list. Then we want to do is mean heap dot push pointer slash val. So that's what pushing is for, and after that we will be just iterating it through. Let's do this one, or it's a little messy, but okay, do this only. Fine. Pointer is equal to pointer dot next, right? So what I did was is we once we came across here, the pointer come across let 0. Then after after that, what we did was right here with this while loop, we moved the pointer from one position to two position, then three position, and so on. Right? Next dot next dot next. So that's what's going on. Next dot next dot. As at every point we are pushing it via this push function. Okay, that's what the step one was. Let's move to step two, that is adding the elements. So for doing that, we'll use a while loop. It is small, so we'll check. So we will keep on removing elements because we want to delete each node and then add it to the output. Delete the minimum node and do that. So min heap dot empty, and we're gonna do it further. So list node. Um, this node is gonna be, now what we're gonna do is we are retrieving the topmost node. Okay, so at this point of time what we are doing in this code, if we have let's say if we have, you know, uh, in the heap, we have, this is the heap. Okay, so what we want is we want to retrieve this node. Okay, and what this node is, so this basically this value, not node, the rather value. So this value we want to retrieve it, and then we want to form a, suppose this value is 2. So we want to form a node, assign a value 2, and add it to the linked list. That's what we are uh, trying to do. Okay, so list node is equal to new list node min underscore heap and doing the top. And why the top? Because the topmost element is the smallest element. So we are creating a new node using a new keyword, and the node node pointer is pointing to the newly created nodes. That's what node is doing. Okay. After that, after that, after that, what we need to do is once we have a node, what we want to add this node to the output list. So for our output list, I'm just going to have some variables declared. List node answer, head of the answer, that's going to be the head of the answer. Next would be list node of currents to iterate through the answer list. Correct. So your node is right here, and what you're going to do is, what you're going to do, let's zoom out a bit and make it a little, yes, yeah, I think that's fine. Now what you're going to do is, if now at this point of time, what you do is create new node, create new node from, so this whole statement is creating new node with the minimum value, because it's in ascending order, right? So we want the minimum value first to be attached to the lists. Okay, so that's the minimum value that's going to be attached to the list in the first place. So adding the newly created nodes in the list. Okay, just we're almost done. Okay, answer underscore head. So if the answer is not equal to null, then what we're going to do is we are going to simply adding a new node to a list. That's what we are doing. Oh, why the hell is that name so big? Answer head is equal to node, and then we are going to do current is equal to node, right? So at this point of time, uh, your answer head is pointing right here, and the current is pointing right here. Current is pointing right here. Okay, so because of this, because if there was no, once you inserted the very first element, this step occurs. Otherwise, if you already have inserted an element and the answer node is pointing to some element that is right here, some node, the remaining step is to, because let's say you heapify it again and you figure out that the next value which comes here is basically 3. Okay, so you want to include a 3 value, right? So what you would do is current dot, you would make a new node and you would make current dot next is equal to that node. Okay, so current dot next is equal to new node, pointed that, And finally, move the current value one step forward and move the current value, current dot next. All right. And this is just, you just created it from the top value, you added the node, and what you need to do is you need to pop. So min underscore heap is pop because this is going to delete the element, and this is like, okay, so this is going to delete the element and heapify your tree. That's going to take O of log of n time. All right. And similar case was for adding the node, for pushing the node in the heap. So in total, it's going for n log n. Right. Each time is going. So this while loop having is running for n times. That means it's going n log n. Okay. At last, when we are done with, when we are once we are done with adding every node from the main heap, our list is ready. Suppose only 3 is there, and after that there's nothing possible, and it's just null pointer, because that's how a newly node is getting created. If the last node is created, the next pointer is pointing to null, and if there is no node and it's get empty, our linked list is ready and we want to return the answer. I think that's pretty clear, and let's try running the code. Okay, let's try running the code. uh, sorry, spelling mistakes. Oh, spelling mistakes again, sorry. Yes, it got accepted. Let's try submitting it. Yes, it got. So the whole approach was, creating the heap from the entire uh, every list, and then popping it out one by one. This approach is really nice. It covers in 2 steps. In Java, you there might be a little different syntax for creating a main heap, but that's what you do in a C++. Any questions? Because I'm done with this problem. And
No.
thank you for staying for so long. Yeah. So shall I stop presenting?
Yes, yes.
Okay, fine. Yeah. Before that, just like last one was that adding takes log n time and deleting takes log n time, and you're doing that for n nodes. So n log n is the whole complexity of it. Time complexity and space complexity is yeah, the space complexity is also mm, that's one of the demerit of this problem, because you are declaring a space right here. Priority queue is you are adding elements, and what how many elements? N elements. So this gives us space complexity of O of n. Right. Now these O of n nodes are assigned are sorry, are allocated in a tree wise fashion, but in total these nodes are n. That way, because of that, the space complexity is O of n, and the time complexity is n log n, because every element is getting deleted and added. That takes log n, and total number of elements are n. It means uh, time is um, o, o of n log n. I think that clears it out. Stop presenting. Wait done with this. Stopping the recording.